Yeah, thank you for the kind introduction, and also thank you to all the organizers for the invitation and the possibility to give a talk. I hope everyone can hear me well and can see my slides well. So yeah, as announced, I will speak about an offline-online strategy for multiscale problems with random defects, and this is joint work together with Axel Mohlquist from Gothenburg. Here's an outline of my talk. So I want to introduce you to the problem formulation and the goals. This will take me rather long to set the goals straight. And then I will introduce this offline-online strategy for so-called Petrov-Galerkin localized orthogonal decomposition, which I will also explain in that run. I will then present some elements of an a priori error analysis, and I will conclude with some numerical experiments, and I will try to be on time to not delay you from the lunch break. So for me, the story of this project is the following motivation. So imagine we want to produce some modern materials like fiber reinforced structures or photonical or phononic or optical metamaterials, so that have enhanced properties over in comparison to standard materials that you know in nature. And then you possibly design these metamaterials like on a sheet of paper or in also using some simulations. You will make up some composite structures, so making up of different materials, and often also a so-called fine scale structure, so that these two materials, let's say, are intertwined on a length scale that is much smaller than the typical length scale of your material block. So imagine we have designed such a material with certain enhanced properties, and we are very interested in that one, and we now really want to produce it. Then there is, of course, a certain risk of fabrication mistakes, so that the machine that's supposed to produce your material is doing not exactly like you designed it. And the material that then comes out of the production process, you want to know whether this has still the properties that you designed it for. So the very general question and background for motivation for my talk is the robustness of material properties with respect to fabrication mistakes, which I coin as defects. Of course, this is a very general task, and I will restrict myself now to a rather limited model problem. Before introducing this model problem like in rigorously, let me give you some notion of it. I will look at diffusion problems where the diffusion coefficient A is a realization of the following form. You have a background multiscale coefficient, so this multiscale nature is indicated by the subscript epsilon, and then you kind of randomly switch on certain defects. So you have multiscale defects as well, and you have something that kind of switches them on. So with a defect probability P here, that will be assumed to be rather small in the following. While this may seem rather abstract, let me give you two concrete ideas how this could look like. I hope you can see this also in the room. So the first one is like a random checkerboard example, where this background coefficient is just white, so constant, in this case 0.1. And then you have small squares of length scale epsilon, and for each square you draw a non-fair coin, you throw a non-fair coin that if it shows tail, which occurs with probability P, you get that this square is a black spot instead of the white one. And here you see an example realization, I think, for P equals 0.1. The other one, the example I want to give you for, imagine this throughout the talk, is the following one. It maybe falls more into what you expect to be a material defect. So your A epsilon is a multiscale coefficient that in this case is made of epsilon periodic, where in each periodicity cell you have a background value of 0.1 and then a small square inclusion. So you have something like this as your, should be imagined as your A epsilon, if you can't see the big picture. And then defect means, so at each of these black inclusions, you now throw a non-fair coin with probability P. And if this shows tail, let's say, and then this defect will kind of vanish. So the value will be set to the background value. So this is something imagining like you want these black inclusions to be printed, and there's a certain failure probability that your printer does not print the black spot, let's say. Okay, so having these pictures, you should keep them in mind for the rest of the talk, because I will refer to them quite frequently. And in this setting, we have now the following goal. We want to obtain approximate solutions U for many different realizations of A. So as a disclaimer, I'm not here considering any specific or talking about any sampling strategies or anything about what to do with your solutions afterwards, whether you want to compute the expectation or other statistical information. I have in mind that I'm in some sampling or Monte Carlo type related setting where I just need a lot of approximate solutions for many realizations of A. And I think this abstract setting occurs quite frequently. And then, of course, for each single sample, we have the problem that the coefficient A has a multiscale nature, as you've seen on the previous slide. And I think I don't have to tell you that tackling this with standard finite element methods is computationally not very practical and often even infeasible. And therefore, we will look at computational multiscale methods. Specifically in this talk, I will talk about the localized orthogonal decomposition. But I think that some of the ideas and problems I want to address also transfer to other computational multiscale methods. Namely, the main challenge is that, let me remind, how do computational multiscale methods often work? They are some sense of generalized finite element method where your ansatz and test functions are no longer piecewise polynomials, but so-called multiscale basis functions that are adapted to your problem at hand. And this in particular means that these multiscale basis functions include information about your coefficient A and that they are different for each realization. And since the main computational effort in a multiscale method lies in the computation of these multiscale basis functions, having to compute them for each realization of A in our setting may still become demanding, even though we can then use coarser meshes than with a standard finite element method. And here I want to discuss like how to reduce this computational complexity in a certain sense by making use of the structure and this defect type picture of A. And I should mention here that that this defect type picture here does not mean that the amplitude of these perturbations is small, but they are in the sense rare in that the overall affected area is small. And we will see how to use this. And as a disclaimer, just taking this deterministic A epsilon as a kind of reference where to compute everything with is not what we want to do, because yeah, it easily does not give good approximations any longer. Of course, we are not the first to address this challenge. So the first 3 points are somewhat a limited overview of what has been done in combining, in how to reduce computational multiscale methods if you want to compute that for many realizations. And since we will, as you will see soon, we'll be in this talk looking at the periodic setting, you can also ask about how is this related to stochastic homogenization and all the numerical approaches that are somewhat related to this. So in computing homogenized coefficients of compressing the expected solution operators, or this large class or series of papers by Lebris and co-workers on so-called weakly random problems that are where our setting exactly falls into. So in order to or to see what we do differently, we are not only interested in expectations of the solutions or the stochastic homogenization matrix. We do not want to compute it. We are exactly interested in the solutions, as I've said. Furthermore, our epsilon, so the multiscale nature, will be small, but we will not consider the limit epsilon going to 0. And this work is largely inspired by these two works about the localized orthogonal decomposition for so-called similar or perturbed coefficients, where this A epsilon, so this deterministic background coefficient, was taken as a so-called reference. Everything was, the multiscale basis was computed for that, and then for the given for a given new coefficient, it was not in a random setting necessarily. It was looked like where is this new coefficient, how much deviating from the old one, and where do we need to recompute our multiscale basis functions. And we will in some sense extend this framework for not having only one reference coefficients, but a collection of those. Okay, before I go into the method, let me precisely formulate my problem. So this is the standard weak variational problem. Here I'm always looking at one single realization of A. That's why I will omit this random parameter omega for a moment. And then we have this variational problem here, where for simplicity our spatial domain is the unit hypercube. The right-hand side F is assumed to be an L2. And as test and ansatz function space, so this U is kind of our reference solution. We allow either the full Hilbert space or some finite element approximation. So this does not need to be computed, but this is like the reference solution we want to compare to. And we take periodic boundary conditions, and in order to enforce uniqueness, everything should have a 0 mean here. So in this setting, we now need to say how this A is chosen. And as I've already said, A is a realization of the following form, and now come into play a bit more of the assumptions. So A epsilon as well as B epsilon are epsilon periodic, which you can write as them being, you have one periodic blueprint, A per or B per, and then you insert x over epsilon in there. We have certain uniform boundedness conditions from above and below on A epsilon and B epsilon, so that in particular any realization of A satisfies the same upper and lower spectral bounds alpha and beta. And in order to fit the periodicity into the domain, we need to assume that epsilon is of the form 1 over n for some natural number n. And then what is still missing is the model for this BP, which is now this random defects model. And it may seem a bit technical, but you should have the pictures I showed you at the beginning in mind. So we have like non-dimensionalized deterministic Q, which is a subset of the unit hypercube, and then you shift and scale it, and these are then all the possible defect locations. And then, so Q is a subset of the unit hypercube, it can be the whole unit hypercube. And then for each of these defect locations, you have a Bernoulli distributed variable B hat, which shows 1 with probability p and 0 with probability 1 minus p, and all these are independently distributed. So this is really like at each defect location, you throw a non-fair coin whether to switch on the defect or not. Okay, having this setting now, we can move to the offline-online strategy. And first of all, I will introduce you to this Petrov-Galerkin LOD, how this is set up. So there's, in a nutshell, one slide evolving about the localized multiscale method, and I hope I can convey you how this is working. So to start with, we are working on a mesh T capital H, which here is quadrilateral to fit to our whole periodicity and unit hypercube setting. But more important, it's assumed to be coarse in the sense that the mesh size capital H is larger than our multiscale coefficient epsilon. So to remind you, doing a standard finite element method on this mesh would yield you some result, but this is this will not be a good approximation of your reference solution. And on this coarse mesh, we introduce the lowest order finite element space. So this is Q1, these are bilinear elements, and with periodic boundary conditions and zero average. Furthermore, we assume that we have at hand IH, which is a quasi-stable, a stable quasi-interpolation operator onto VH, so it should be a projection for simplicity and enjoy the standard approximation and stability properties, so something like an Oswald interpolation operator, for instance. And by VF, we denote the kernel of IH, so all the functions that are from the space V that are mapped to 0 by IH. And these are the so-called fine scale functions because they are kind of not seen by this finite element space VH. They cannot be represented in that. That means they have some type of oscillations on a scale smaller than H. And then we first need another technical concept, namely that of an M layer patch around any element T of our mesh. So this is simply taking your element T, and then if you have your discretization, I hope I can draw it, taking, whoop, this shouldn't be, this should be here, then taking, if I just take T and one element around there, this is my U1 of T, for instance. And then, so this is some sense of accounting how far you are away from your T in multiples of the mesh size capital H. And then we introduce kind of the localized kernel space, which is VF UM of T. So these are all the functions lying in the kernel of the interpolation operator, which are 0 outside the patch. And having established these, we can now introduce so-called correction operators that build an essential ingredient in defining our multiscale method. The correction operator CM, M being related to this layer parameter, and I explicitly denote here the coefficient that it's related to in brackets here. So this correction operator can be is written as a sum of local contributions CMT, and each CMT has now 3 properties. The first 2 are encoded in that it maps to this space VF UM of T. And this means that CMT is first of all a fine scale function by lying in this kernel space. And second, it's quasi-local, namely that its support is contained in this patch around T. So it's not localized to T itself, but to a small patch around it. And the third property is defining the CM of T via a kind of projection type problem. So solving this local small problem on the patch UM of T, where this coefficient A enters. So there you see also why the CM of T depends on A. And this is a fine scale problem here, but since we are on a local patch, we can afford to solve this on a fine scale discretized mesh. And with these correction operators, we can now define our localized orthogonal decomposition, and we will do this in a Petrov-Galerkin formulation. So we seek a solution in the standard finite element space such that it satisfies this variational problem, where I recall that this fractal A was the standard bilinear form. And so the test functions are still the standard finite element functions, but the answered space has now been modified to be this kind of multiscale space. So in order to assemble kind of the stiffness matrix, you have to compute 1 minus Cm of A times lambda, where my lambda is any of the basis function of my finite element space. So I will talk about hat function, although with Q1, this is maybe not a real hat here. And I will abbreviate this thing by the bilinear form fractal B here. And in fractal B, you should note that the coefficient A enters like twice. Once in this that it's like A grad, and the second one that it enters also in these correction operators. And then we can also already note that by this by Cm being defined as this sum of CMTs, we can write this whole thing as follows, of course. And this will then, in this you can use to define your local bilinear forms Bt of UMHV, because you can restrict now everything. If you insert these hat functions, you can restrict things to the patch and the elements. And I will talk about this in a moment a bit further. So this is the standard formulation of the Petrov-Galerkin LOD here. And you see that you have to compute your correction operators for each coefficient anew, and then have to solve a rather small linear system, because this the dimension of this space and these matrices is rather small. And we will now discuss how to reduce the computational complexity involved with computing all these correction operators for the different realizations. And this is exactly the offline-online strategy, where I first want to give you the general idea, and then I will go into the maybe a bit more technical details. So the offline phase, this is done once in the beginning, before you do this for all the before you start for the different samples. So once you build, you select deterministically so-called reference coefficients AI that in a certain sense will build a certain basis. I will come to that in a moment. And then for each of these reference coefficients, you pre-compute and store the LOD basis functions. So remember, lambda are these are the finite element basis functions, and you compute this lambda minus C of AI, and there should be an M here, Cm of AI. In fact, we will do it slightly different, but I will come to that in a moment. This is what you do once in the offline phase, and then in the online phase, for each given sample where we want to have the approximate solution, you first of all find coefficients such that you can write it as a linear combination of the AI, and the selection of the AI will yield that this is always possible. And then you approximate this Cm A lambda by the things you pre-computed in your offline phase, namely by the linear combination of the Cm AI. And you should note that because these Cm are defined by a local some sort of projection with respect to the AI, it's not at all clear from the start that this approximation here is a good approximation, because yeah, you simply you write your solution, you have a coefficient that is the sum of coefficients, but then it does not mean that the solution of an elliptic of the projection problem is also the sum of the solutions. This will in general not hold, but in our setting we can show later on that this is still a good approximation for small defect probabilities. And this approximation then allows you to have a rapid assembly of your stiffness matrix for the LOD, because that's essentially what enters there, and you then only have linear combinations of pre-computed things. And let me now go a bit more into the details. So first of all, to start with the offline phase. And this offline phase, because of the periodicity and structural assumptions, we only have to do it for one single fixed element T. So we fix an element T and its M layer patch around it. And then we have a number n of possible defects in there, and J is the corresponding index set. So this number of defects may be rather large, but it's always small, or it's in general smaller than the number of possible defects in your whole computational domain, because this UM of T you should imagine as being a small subdomain of the whole computational domain. And then you choose the offline coefficients as follows. A0 is just this background coefficient A epsilon. And then from 1 to n, you go through all your possible defects, and one by one, you switch on one single defect. And that's also illustrated for the two pictures I've shown you at the beginning down here. So this is this random checkerboard. So there, this is A0. And then A1, A2, A3, you simply switch on one black spot at each possible location. And this, of course, continues further. And this is here in this inclusion type setting. So there A0 is this with all the black inclusions, and then A1, A2, and so on, you erase one single inclusion, and you do this all through all the possibilities in your UM of T. Only the single defects. And for these offline coefficients, we pre-compute these local stiffness matrices. So I recall that I've already shown you that this fractal B, this bilinear form, and in some sense I will use bilinear form and stiffness matrix in some sense in a similar setting, can be written as a sum of local contributions, and this one looks as follows. So these lambda j, lambda k are my basis functions for the finite element function, and then you have an integral here over the patch and something related to the coefficient and its correction operator. And this is a small rectangular matrix because all the non-zero entries of this local contribution here. So for this lambda j, you only have to take those basis functions associated with your element T. And for the lambda k's, you have all the ones that have a non-empty, whose support is somewhat contained in UM of T. So this is a small rectangular matrix that is easy to store, and you can afford to store this for all your reference coefficients in general. At least that's what we do. And then the offline phase is done so far. We've pre-computed and stored all this, and we move to the online phase. So there we have given a sample coefficient, so a realization A, and we go over all our elements of the mesh now. And then for each mesh element, we first of all find coefficients mu I. So these depend on the mesh element T. I omitted this here for simplicity. We find these coefficients such that they sum up to 1, and that on the patch UM of T, A is given as the linear combination of these mu I, AI. By the choice of our AI and the structure of the coefficient A, this is always possible, and it's also easy to find these mu I. So there's no big linear system or so we have to solve. We basically have to look at the given realization of A and see where are its defects located if we're restricted to the UM of T. So kind of which defects do we need to switch on in this decomposition here. And then once we have determined these mu i's, we can locally simply do the linear combination of the mu I and the pre-computed stiffness matrices from the offline phase. And this defines our local new stiffness matrix B tilde T. And the global stiffness matrix is then B tilde by summing up over all the elements. So this is an approximation of the stiffness matrix for the Petrov-Galerkin LOD associated with your sample coefficient A. And then we compute this, our offline-online solution U tilde HM as the solution of this variational problem. So this is, as I said, a rather small problem that is easy to solve. And it's of the same dimension as if you would do the Petrov-Galerkin LOD for the coefficient A directly. So there are now two questions. The first one is, in how far is this U tilde HM a good approximation of the U? And the second one that I will address in the numerical experiments is, how far can we save computational costs from this? And there I want to recall that if you take like your Petrov-Galerkin LOD or some variant of it before studied as a benchmark in some sense, you only have to compare up to this assembly step, because solving the solving step, the last one, will always be, or we will consider that this is always the same with always the same cost. So let me now present you some elements of how to evaluate the error between the reference solution and this U tilde HM I just defined. So let's start with the one-dimensional case, because things are a bit easier in that case. Namely, first of all, in the one-dimensional case, you can do everything purely local. So your UM of T is always can be chosen as your T. And then by n defect, I denote the number of defects in T that are there in T for the given realization. So how many things are really switched on. This is, of course, a random number in some sense, strictly speaking. And then I write this n defect as the fraction theta defect times the number of possible defects that you could have at maximum. And theta defect is then the maximum over all the elements. So if this is confusing you, it's not stochastically correct, but you can imagine to be theta defect somewhat related to the defect probability P. And then we have the following result on the kind of consistency error. So between the stiffness matrix for the Petrov-Galerkin LOD for this single sample. So all my estimates will be single sample estimates, and the offline-online strategy stiffness matrix that comes out. And the bound is as follows. You have something that depends on the contrast. You have this volume of the non-dimensionalized defect size in there. And then you're basically quadratic in theta defect, or in, I may say, in the defect probability, where the linear term is multiplied with the small constant epsilon over h. And this consistency error estimate then also leads you to, by standard strong type arguments, to an error estimate between the exact solution and your offline-online solution. That's why I will focus on this consistency error in the following discussion. And the one-dimensional case here uses that you can write your B and B tilde in that case as a standard finite element matrix with a modified coefficient. And this modified coefficient is like taking harmonic averages of your coefficient on the scale h. And then in order to analyze everything, the only thing is you have to compare the different harmonic averages, and that's with a lot of calculation on paper, you can then come up with this rather explicit bound here. In higher dimensions, this is not that easily possible, but we have the following result. Let me start from the end. So again, the consistency error can be bounded by the maximum over all elements of a local quantity ET, which has this rather lengthy looking form, but it in essence requires to solve a small eigenvalue problem, and all that you need to know in order to set up this eigenvalue problem is the given realization coefficient A, of course the mu i's and your offline coefficients, your reference coefficients AI, and the local correctors for all the AI. But this is something that you compute in your offline stage anyway. So that's why we call it a computable error bound, because we do not need to compute the correction operator associated with A in order to evaluate it. Because if we would compute that, we could also do a Petrov-Galerkin LOD for the A directly, and our offline-online strategy would not be needed. And so we only need things that we have available directly, namely this coefficient A, or that we've pre-computed in the offline phase. And in the paper, we comment more about how to efficiently implement this. And this error bound is also a bit more general than the setting I considered, because it includes this A bar, so this sum over the mu I AI, which is the same as A in our setting. And there you could even simplify this bound a little. That is already all I wanted to tell you about the error analysis, and I would like also, with respect to time, I would now like to come to some numerical experiments. So first of all, in the one-dimensional case, we looked at this random checkerboard, and we computed root mean square relative L2 errors over 500 samples for different mesh sizes and different defect probabilities here. And we could see this quadratic increase in the defect probability that somehow, in some sense, was predicted by our theorem as well. And we could furthermore see that we have, if you go up to, I don't know, defect probabilities of 10 or 20%, we still stay between, below 5% of relative L2 error. And in the two-dimensional case, we now fixed a mesh size and an layer parameter, and we did the same random checkerboard thing again. And we again see this increase in P, and here we could see that up to defect probabilities of like 10%, which is already quite a lot, we have still what we would see as an acceptable relative L2 error, namely only a few percent, like 3%. In the second numerical example, I will look at this inclusion picture in a more general setting here now. And now I do not want to illustrate somewhat the parts of our error analysis, but I want to look at how different defect types influence my results, and also like how how robust things are, not robust, how different defect types influence how difficult it is to approximate how different the solution is if you introduce a defect. In the first row, in the top row, that's what I will call change in value. So the top left picture is exactly what I presented at the introduction, that defect means that you set the value of your inclusion to the background value. In the middle picture, we set it to some different value that is even smaller than the background value. So the background value is 1, the inclusions is 10, and here this white is 0.5. And in the right picture, it may be hard to see from the contrast. We have a defect here, and it's intermediate grayish, which should signify that we took, like, I think it was the value 5, so something in between the background and the inclusion value. And here at the bottom, you have different changes in geometry. You probably can see the left picture there. Defect means that my inclusion becomes a bit larger. In the right picture, it becomes smaller, but in particular, its center is shifted. And in the right picture, it's probably hard to see, it changes from a square to an L shape. So let's compare things in a specific setting. So first of all, when changing the value, we see if we do something like the intermediate value here in green, the error is really, really low. But also with the other value changes, the error is very small, of 10 to the -3 up to less than 10 to the -2 here. So this change in value, if you also compare how things are here on the y-axis, seems to be easier than the change in geometry. And for the change in geometry, especially this, what I call fill, so making these inclusions larger, seems to be the hardest case. Still, I want to first highlight that up to defect probabilities of 10%, or even 15%, we are still only on a few percent of relative L2 errors. And also that this model fill is the hardest is, I think, not very surprising, if I may go back a moment, because in that model, you can have that two defects kind of connect, or two inclusions connect by being both a defect. And this, of course, changes somewhat the topology, or not the geometrical structure of your inclusions, and you get something more in the, you can get like small channels or so, and this of course explains why the solution may change more drastically for that setting, I think. And with that, I also having a look at time, I want to already sum up and conclude. So I've presented to you an offline-online strategy, which was based on the localized orthogonal decomposition. As I said, I believe that ideas may be transferred also to other multiscale methods, but I have not looked at it. The offline computations were done for representative defects, and which then allowed an online rapid assembly for each sample by just taking linear combinations. And there I should maybe say that a preliminary runtime comparison for us showed that already for like 10 samples or so, our offline-online strategy was really able to be much faster than what we had as other implementations not using this offline-online strategy. I presented to you an error analysis with a computable upper error bound, and we saw, besides what I told you about the computational complexity, also a good error performance, also accuracy for, I would say, in a medium contrast setting, and defect probabilities of, let's say, up to 10%. Of course, there's room for debate about the exact percentage here. Of course, in the future, we would like to extend this to more general randomly perturbed coefficients, especially overcoming, in some sense, this periodicity assumption, which then entails new questions. For instance, already in this periodic setting, whether this choice of offline coefficients is really the best one. It worked for us, but we still need to understand things about it. And then it's well known that multiscale methods, and in particular the localized orthogonal decomposition, have tight relations to the areas of domain decomposition and preconditioning. And maybe these ideas of offline-online strategy in this random defect setting may also yield to new results and approaches in these areas. And with the reference to the John article, where you can find all the details, and advertising that if you have students being interested in working on multiscale methods, I have open positions available. I would like to thank you for your attention.